Good day once again, class. So for these presentations, we are going to talk about hypothesis testing given a proportion or percentage. So going back again to your confidence intervals for one proportion or one population proportion, let's say at 95% confidence. So we know that we have the estimator, the sample proportion p hat, then plus and minus our margin of error. Because we want the 95% confidence, then we use the critical value of 1.96, then multiply to the standard error of the proportion, wherein this is the proportion, the sample proportion times its complement divided by your n. Now, when you look at the formula for the z-test for population proportion, so we need to take the difference of the sample proportion and the hypothesized population proportion p. However, class, there is a slight change. Your standard error now, instead of the sample proportion, we use the population proportion or the hypothesized population proportion as part of your standard error. And the critical value is 1.96 because we want it to be 5% level, which is the complement also of the 95% confidence. This is our basis class, whether or not the computed z value, okay, is significant to say that the null hypothesis is to be rejected or not. Similar to the concept again, class, of your hypothesis testing for one population mean. So it's only the formula that is different, class. And in this case, we are not using the mean and the standard deviations, but what we are using now will be the sample proportion. So most often than not, class, the sample proportion is not given in percentage, but it is given in how many, okay, we observe out of the population or out of the sample. Then we just take the ratio multiplied by a percent, and that will be the sample percentage. But since it is a proportion, we do not need to multiply it by 100%. So it is most often than not, it is a decimal value. Where your P here is the population proportion, this is the value that is used in the statement of the null hypothesis. And your Q is the complement of your P. So if your P is, let's say, 1%, then your Q is 99%. So it's just the complement, class. So the formula that we use is this one. Ayan. So it's similar to that of your T value class or the T tests. We call it the Z test class because we use the Z. So again, the same, similar, we have the same critical values to use. If you want the level of significance alpha to be 5%, then use the positive and negative 1.96. If you want the 1% level of significance, we have to use the positive and negative 2.575. Okay, so this will tell us, class, whether or not we have to reject or fail to reject or do not reject the null hypothesis. And of course, we always have our graph so that we can easily identify whether or not we reject or we do not reject the null hypothesis. Now, again, if your null hypothesis is not rejected, the conclusion is the statement in the null hypothesis. But if you rejected the null hypothesis, class, the conclusion is the statement in the alternative hypothesis. Okay, so similarly, the null hypothesis contains equality while the alternative contains not equals, and we are using the two-tailed test. Okay, so we have here an example. So atorvastatin is a drug used to treat high cholesterol. So in a clinical trial, 64 of the 863 treated subjects experienced headaches. So in other words, it might be classed that taking atorvastatin, one of its, let's say, not good indicators is that those who are taking such will experience headaches, which is actually commonly, okay, experienced as a treatment So we are going to test the claim that the percentage of the treated subjects who experience headaches is not 10%, then use 5% significance level. Now, we want to find out, class, that based from the sample of 64 of the 863, this one is not equivalent to 10% because this is the claim. Okay, so what we're going to do is identify the given data. So it's easy because most often than not, we only have 3 to 4 lang. Then all we have to do is to identify them. So the total number of trial or sample is 863. Of the 863, 64 experience headaches. Then if you take the sample class, the sample proportion, you divide 63 by 863, 64 by 863, and that would be 0.0742. So typically, class, I am using up to 4 decimal places, but it's also okay if you use up to 3 decimal places. So I will be using 4 decimal places for this one. So it means, class, that the percentage, the actual percentage of experiencing headaches is only 7.42% against the 10%. So we want to find out whether 7.42% class is the same as 10% or it is different from 10%. Okay, literally speaking, class, they are really different, but we are given the significance level. It might be that, let's say for example, class, if it is not significant, it means that 7.42% is the same as 10%. So how does that happen? It means that we have the sampling error. Okay, but if the 7.4442 is not really equals to 10%, it means that it is really less than 10%. That's the actual value. Of course, our hypothesized proportion is the 10% because this is typically found in the claim, and its complement class is 90%. So if 10% is 0.10, then Q is 0.9. Okay, so we are now ready to substitute this into the formula, but first we have to establish the null in the alternative hypothesis. Okay, so according to the claim, the percentage of treated subjects who experience headaches is not 10%. So there is the word not 10%, meaning it is not equals to 10%. So the claim, class, is the alternative hypothesis. Then we can formally write our null and alternative hypothesis because this is where we are going to write the conclusions later on. Which of these two is the correct conclusion? So again, the null hypothesis always contains equality, so we can rewrite it as the percentage of treated subjects who experience headache is 10%, while the claim is your alternative hypothesis. Then, we are ready to substitute all the values, class, into the formula. Okay. So, going back to the data that we have, then we are going to substitute it. Okay. Then, again, as I said, in your denominator, always round your answers up to 4 decimal places. Then your final answer should be 3 decimal places. Then the computed z-value, class, is negative 2.529. So again, if it is negative, it means that 7.42 is really less than the 10%. Okay, that's the reason why we have a negative. So we want to find out whether 7.42% against the 10% hypothesized is really different at a certain level of significance. So this is the result already, class, of the computed z-value. So we can choose what is the critical value because we are given at 5%. Then we have to use positive and negative 1.96 as our critical values. Then we plug where can we locate our z. So our z value, class, is negative 2.529. This is what we solved earlier, and it is found less than the negative 1.96. So we can now see our decision right away that we have to reject our null hypothesis. Okay, so because we reject our null hypothesis based from our computed z value, then our conclusion, class, will be the statement in the alternative hypothesis, which is the claim. So therefore, because we rejected it, then our conclusion at 5% level, the percentage of treated subjects who experience headaches is not 10%. So the claim is correct, class. And in fact, it is less than 10% because the negative z-value indicates that the percentage who experience headaches is actually less than 10%. 7.41% is less than 10%, class. So that's the reason why we have to reject that it is equals to 10%. In reality, it is indeed less than 10%. So if that is now the result, then maganda siya, class, yung atorvastatin kasi nga the percentage of people who are taking such, the who experience headaches is not actually equals to 10%, but in fact less than 10% only. Okay, so that's how we solve, class, hypothesis testing that is based on proportion. You notice, class, that the process or the steps are the same, only that the formula is different. So another example here. Okay, so in another example, class, so in a study of the accuracy of fast food drive-through orders, McDonald's had 33 orders that were not accurate among 362 orders observed. So use 1% significance level to test the claim that the rate of inaccurate orders is equals to 10%. Does the accuracy rate appear to be acceptable at 10%? So in other words, class, is that the actual proportion or percentage based from a sample of 362 is 33. So we want to find out whether or not this proportion is really equals to 10% or it could be less than or greater than 10%, and does the accuracy rate appears to be acceptable at 10%. So granting that the manager will only allow up to 10% in accuracy so that it can be acceptable. Other or any percentage greater than 10% will not be acceptable anymore. So first, we are going to identify the given data. So we have 33 orders out of 362. Then we use 1% significance level. Then, of course, the hypothesized percentage is 10%. So if we're going to identify further our data, so if we divide 33 by 362, we get the sample proportion or the percentage. So this will give us 33 out of 362 is about 0.0912, or that is 9.12%. The hypothesized proportion class is 10% or 0.10, and its complement is the 90% or 0.9. So we want to find out, class, whether or not 9.12% is the same as that of the 10%. If it is not, then we could say that it is less than 10%. Then it is still accepted, the accuracy rate. However, if only the actual or the observed value or the proportion based from the sample is more than 10%, then that might be questionable already when it comes to accuracy. Okay, so we want to find out whether 9.12% is the same as 10% or it is not. Because if it is not, class, then the better. It is really less than 10% as the inaccurate rate. So again, first, we are going to establish our null and alternative hypothesis. So the claim says that the rate of inaccurate orders is equals to 10%. Because it contains equality, class, so the claim becomes your null hypothesis. Okay? And the alternative hypothesis is the opposite. It contains not equal, so you can just rewrite it as the rate if inaccurate orders is not equals to 10%. Okay, so one of these hypothesis is the correct one. So remember, the null hypothesis always contains equality. So we are now ready to substitute all the necessary values, class, or the data into the formula, and we can solve for our z-value. So in this case, 0.0912 as the sample proportion minus the hypothesized proportion, we have a difference of negative 0.0088, or that is less than 1%, or 0.88%, divided by the standard error of the proportion. So again, always um, up to 4 decimal places. Then your final answer class will be to up to 3 decimal places. So the computed z-value of negative 0.557, this is the one that we are going to compare against the critical values at 1%. So because the level significance alpha class is 1%, then we have to choose positive and negative 2.575. Okay, so this is the one that we're going to put into our graph. Then we can, given the critical values of negative 2.575 and positive 2.575, and we can locate the computed z-value class of negative 0.557. So we can easily see now our decision that the computed z-value of negative 0.557 is in the region of the non-rejection. So it is between the critical values class. So our decision now, of course, is do not reject the null hypothesis, since the computed test statistics of negative 0.557 is not within the critical region. So therefore, what would be our conclusion? So the conclusion class will be the statement in the null hypothesis. So at 1% level, the rate of inaccurate orders is really equals to 10%. Okay, so it's not beyond 10% class. So because there is another question, does the accuracy rate appears to be acceptable? So since the inaccuracy rate is 10% or less, then it is acceptable if the cutoff rate is 10%. So if only the sample proportion is more than 10% and we found out that it is significant, then that's the only time class that we could say that the inaccuracy rate is more than 10% and it would not be acceptable anymore. So I guess you've learned again uh, the lessons about hypothesis testing on proportion. And once again, so thank you. And this will be our last lesson for this semester class. So thank you for your time staying with me, class, and hopefully to see you in class face to face, okay, during your visit to the university. Thank you.